you know, just a review that up till now, most everything we've worked with has been vector data. Lines, points, and polygons. The roads were lines. The surface areas ended up being polygons. We had points for hospitals and schools, all that kind of stuff. So we're going to move in for the next 3 weeks working with raster data. So we're going to work with raster data today in the form of elevation data. In the price tutorial, they use raster elevation models to create slopes and view sheds. We're going to turn polygons into raster data, so you can do kind of do you remember that snail analysis that you did all with vector? So with price, you're going to do the snail analysis, but all with raster, and you're going to find out like, oh my God, it's so much faster. And that's the adage. Raster is faster, but vector is corrector. That's, yes. So remember that vector is corrector. You can make an outline of a pond much more accurately with vector than you can with raster, right? But with raster, I can stack several different layers, all with those grids stacking exactly one on top of the other, and then do some really cool analysis with that. So a raster is that kind of grid cell, right? So we have a cell or a pixel, and we talk about rows and columns of data. We talk about the cell size is the resolution. So if I have a 100 meter by 100 meter cell, that's a lower resolution than a 10 meter by 10 meter, or in LiDAR where it's 10 centimeters by 10 centimeters. Oh yeah, that's, you know, that's huge resolution, right? But the smaller, the better the resolution, the bigger the file. So these things can be massive, right? And that can be a problem. So when we talk about a cell, there's only one cell that has XY registration with it, and that is this north, the northwest corner cell is given a lat long, and then everything else is figured out based on the size of the cell and the row and the column. So as long as I know my starting point, I know how many rows and how many columns and the size of the cell, I can, you know, make my grid cell out from that. And we don't have to know that. That's all within the data of the raster, but you do want to be able to find that information if you needed it. So when we talk, sometimes you'll work with data that will ask you for the extent of your raster, and so they're looking for, hi Ryan, the maximum northern extent, and then the minimum southern, and the maximum east and the minimum west, or the XY coordinates for that kind of bind that raster extent. And that's something that Ryan's working on right now, because we're trying to grab image rasters for certain places on the coast, and so he needed to know the extent of the area he wanted to collect using lat long for all four corners. So that's kind of one way to think about your raster extent. When you open up raster data, you can open up the source data and it will give you information. And I think we did this in Price Chapter 2. She had you look at all these different kinds of rasters. But it tells you that there are, in this one, 679 columns and 937 rows of data. Each cell, each pixel is 30 by 30. And I don't know what, 30 inches by 30 inches, 30 feet by 30 feet. I have to move on down to the spatial reference. And it says, oh, 30 meters by 30 meters, because I see that down here. And then it tells me the pixel type. So this is floating point, which means it's a decimal, right? And decimals will have their own interesting problem with them. We'll work with those a little bit today, and you'll get to see some ways to change a floating point raster into a non-floating point raster so that you can do some analysis with that. So you can get rasters in a TIFF, which is an image. When we entered the JPEG, image to do our data manipulation and georeferencing, that would have been a raster format. We took that image in as a raster. The digital elevation models are rasters. There are lots of other types of rasters that you may run into. Mr. Sid and ERDOS is a remote sensing program that has raster data called an IMG. But we're going to work mostly with DEMs, and then Esri's rasters are called grids, G-R-I-D, and I don't know why that's not on here, but it should be. Okay. So one of the cool things about a DEM is that once I have the digital elevation model, I can create other rasters based on that elevation. So for example, I can create a hillshade, which is this image in the upper right, which gives you the perception of elevation. You can kind of see that shadowing and shading. I can create slope. I can create aspect. So if I want, I think the lab you're going to do to site a cabin in Sturgis is to find a cabin on a fairly flat area but has a southern exposure. If I wanted to site solar farms, this would be something that I would want to be able to find flatter areas perhaps and with a southern exposure. If I want to know what kind of trees I need to plant or what kind of gardening I might do, I might need to know aspect for that. So you can also create flow maps. So a lot of the stream data is created from a DEM. So if I know where the slope is and where 2 pixels come together at a low slope, I can start to model runoff or model streams. So, and then you're going to be able to create or use thematic rasters. So this one is a raster of geology. So you'll take a Polygon raster today and turn it, or Polygon geology Polygon, and turn it into a raster of geology. Blah blah blah. Okay, so what? Whew. Yeah, that's the word. Okay, so when you're comparing the two, you have to think about vector data is compact. The structure is very complex. So if you think about all of the XY coordinates that need to go into a road file, every vertice on that road or every segment on that road has at least 2 vertices, the beginning and end vertice of that segment. If you're doing I did glacial maximum, so I digitized all the glaciers from maps, and so every curve had multiple vertices, so very complex. The topology, or how those things, how those polygons line up or lines are very explicit. There's no topology with raster because every cell is inherently connected to its neighboring cells. The resolution in a vector is by your coordinate system. The resolution in a raster is by the cell size. So you get less detail with raster and much more detail with vector, but the analysis with raster is much, much easier. Moving your data around can be a lot slower just because the files are big. Okay, so just thinking about what's the right data type for the job. So one of the things you're going to need is to convert. Actually, not. That was. Oh yeah, actually yes. Thank you. I have quality control in the room today. Thank you, John Paul. So one of the things that Price talked about in the chapter 2 was continuous or discrete data. And so continuous data is data that maybe you can think of as changing smoothly over the landscape, or there always is something. So there's always an elevation, there's always a slope, there's always an aspect. Precipitation is considered continuous, but I mean it doesn't have a hard and fast edge, I guess, to precipitation, and that's why it might show up on the continuous list. Discrete would be soil polygons or geology polygons or roads, land use. So we're going to work with both types of data in this tutorial. And then you can symbolize them based on, is it categorical, is it a continuous where you want to use a stretched symbolization, or is it discrete where you might want to use a unique value. And again, we'll use both of those in the lab today. Okay. So in this example, you can see, I don't know if you can see that from where you're sitting, but you can see this Esri line vector, and that line has been converted into a raster data set of roads. So if I wanted to kind of pull out, maybe this is soil type. If I wanted to pull out what kind of soil the roads are running through, I would need to convert these roads into raster, line it up with this raster data set, and then I could find the type of soil each road is running through and do some analysis that way. So I think that actually this may have been stolen from the Esri tutorial that you're going to do. So if I wanted to look at tornado damage, I might use raster data because I could get satellite imagery to kind of show large areas. And it would also let me stack up rasters based on early images compared with current images, and then I could kind of look at where the tornado swath had gone. Of course, if I wanted to look at the location of museums in the area, I could use vector data for that. So just kind of different typical processes. So when you go through the lab or the tutorial, she's going to have you set up your environments. And this is a really nice way to kind of coordinate where data is being stored. So it sets your default workspace. So she's going to have you create a lab 8 or a chapter 8 results geodatabase. And she says to do a personal geodatabase. I would just get in the habit of doing a file geodatabase. And then you set the processing extent, and that means how big is the raster that you want to look at. So maybe I have 2 different size rasters, and one of them covers Lane County, and one of them just covers the area around Eugene, and I really only want to analyze Eugene. So I could set my processing extent to the Eugene raster. So that means all the other rasters will sort of mentally or virtually be clipped to that Esri or to that Eugene raster. And that kind of sets my new extent. I can also set the cell size. So let's say I'm going to collect raster data and create slope data. So I can choose, I always want my export or my output data to be the same as my Eugene raster. So you get to set all of these so that you don't have to keep setting your raster size and your extent every time. So this is kind of like your geodatabase or your processing workflow. Let's see. So when you open this lab, you're going to see that there is a digital elevation raster that's symbolized from high to low elevation. It's symbolized with a stretch classification. And it looks like these are integers. It says low is at 872, high is at 1956. But actually, that data is float. So when I looked at the labels of that data, I see that the data really is 954.715 up to 1620.000. And so they have taken the data and then typed in what they want their low and high values to be. It doesn't really reflect what the value in the attributes or the actual raster is. So this is float data. So for the snail habitat, you only want the elevation that's between 12 and 1600, right? And I'm sure I didn't remember that from the first thing. But if we were working in vector, we could open up the attribute table and select data that's, greater than 1200 and less than 1600. But with raster data that's a float, you can't open the attribute table. And I wonder where I put that. Hold on, let me pause that. Are you going to let me pause? So when you open up this data, you're going to set the environments. And I'm going to go ahead and put the workspace to the geodatabase that I created, so that if I mess anything up, it doesn't mess up the data, which I've been known to do. Oh, for goodness sakes. Okay. Classes. GIS classes. 246. It's like... No, I know where it is. Wait. There it is. Ha. Okay. So I'm going to set the current workspace to that, and then I'm going to set the results or the output workspace to that, and there we go. Okay, so what I was saying was, I'm going to go ahead and close the roads. This elevation file looks like it's an integer, right? 872 to 19 whatever. If I right click this, and I can't open the attribute table because this is float data, and with float data you can't see the attribute table. But if I go to properties, and instead of stretched I choose classified, I can see that the attributes really are decimal numbers. And that's why it stretched. Let's go back to stretched. Yeah. And here's the values. The stretched values show the decimal, but somebody just labeled them. I could label this 2000 if I wanted, and change it on here. So they're just making that label easier for someone to read and interpret. I don't need to have all those decimals in there, and so that's why that looks a little bit deceiving. Okay. All right. Oh, did I lose that now? Let's see if I can put that up. All right. So you can't select those data to convert them. Okay, so now where am I? Does one think? I'm there. Okay. So integer rasters have what's called a VAT table, and with a VAT table you can actually open and take a look at them. So I'm going to add one from my results file. These are all the rasters I created in 2 hours the other day working with this. So here is my elevation range, and that's a raster. And now I can open the attribute table because the values are not decimals, they're just integers, and I can look at that. So this elevation range of 1, there are 166,641 cells that have that elevation value. I wish I could just go back and forth, but I don't know how to do that. Okay. So when you try to open up a raster data and that attribute table is grayed out, you know that you're working with a decimal, and in order to do some analysis you may need to convert that, and Price will have you do that in this lab. So sometimes integer rasters are whole numbers, and often they will represent categorical data. So what I'm going to do with that elevation data is I'm going to turn that data into 2 categories. One being all of the grid cells that are within the 1200 and the 1600, and 0 all of the grid cells that don't fit anymore. And so my categories are good elevation, bad elevation, and they're going to be numbered 1 to 0. So I'm going to kind of ignore all of the actual elevation details, and I'm going to find just those cells that fit what I need them to do. You're going to find floating points as the base raster data for things that are continuous, right? So they're not discrete from one cell to the other. And so you're going to have that with precipitation, with elevation, with slope, with aspect. You'll find floating points as part of that. So when you have floating point data, the attribute table is not generated, and that's why you can't see that. So one thing, when I converted, when you convert that elevation to yes, no, or good elevation, bad elevation, you lose some of the detail, right? But it also makes it able for you to work with the data. So we're going to do that using this process called Boolean Overlay. And you end up with this true false. So the state and the values of 1 and 0. So I'm going to put up, I'm going to have the Boolean overlay look just at my elevation data, and I'm going to say elevation greater than this equals a 1, and all the other elevations equal a 0, right? So let's see. I can do that with one cell, or I can do that with multiple cells, and you're going to get to practice with both. So in this instance, when I open up the data and I go to reclassify it, I'm going to see all of the old values, and there's new values that now turn those ranges into an integer. So the old value from 954 to 1057, I could have a new value be 1. So I could end up with integers, but I want to go one better than that. I want to change it to this 0 and 1 so that only these values get a 1, and I end up with this reclassification of yes, no. So that the green are the good elevations and the zeros are the poor elevations. And in ArcGIS, you do that in the toolbox. Open toolbox. Come on. And you want to make sure if you're working at home that your extensions for Spatial Analyst are on. Come on. There we go. And mine, I think in the lab, I set them all so they're good. And you're going to go into Spatial Analyst and reclass and reclassify. So I want to say, okay, give me that elevation data, and there's all of those datas, and I'm going to hit this classify. I'm going to go to equal interval, and I just want to set it into 3 intervals. One is above, and the other is everything after that. So you're going to go ahead and set that. And let's see, I don't think I have the directions for setting that on here. Yeah, I think I do. Let me go back. So let's say I want this to be 1200 and 1600 and leave that at the top there. I'm going to now go back to, I don't know why they go back to that. Oh, I know, I set it to manual. Here we go. 1200. You'll have to follow Price because I don't remember exactly what her, yeah. I'm going to do that. And then I'm going to change this one to 0. This is my keeper. Oh, it worked. And then this is my 0. And I'm going to do it on the value field, and then I'm going to have it go in to here, and it's going into the right folder. Oop. Yeah, woohoo! It's that kind of day. Okay, come on. And then I'm going to say okay, and this should go pretty quickly. We'll see. Maybe. It's thinking. Oh, there it goes. Yeah, so I took that elevation data and now it's reclassified into 0 as the elevation I don't want and 1 as the elevation I do want. And so you're going to go through that. And then you're going to take this, this geology data and create a polygon out of that. And you have all of these attributes in the geology data. And so the process says, which one of these do you want to keep? And so you want to keep the name of, for this exercise, you want to keep the name of the geology. And so you're going to do that with the conversion tool. And I'm going to turn on the geology here, and I'm going to go back up here to the conversion, and I want to convert to a raster from a feature. And I don't know why they don't call it a polygon, but they just call it a feature. So my input is geology, and they said to use the name. My output cell size should be the same as, oh, I didn't set, I didn't set that in my, where's my elevation? I didn't set that output cell size as in my setup environments, which this should say 30. When you do that, it should have that already in there. And then this is going to be geology. And I'm going to say OK. And so now I took that geology, and it is now a raster. And I can say now that there are 62,881 grid cells that are of Cenozoic soil type, right? But maybe I only want to keep the limestone. And Price says that Madison limestone and Upper Paleozoic are the limestone categories. So I could reclass that to yes, no. Somewhere down here. Spatial analyst, reclass. So I can put in, ooh, does anybody see a problem? That's selected. That could cause me problems. So I can set this up. Now this one isn't a number, so I can't hit the classify. So I'm just going to go in here and change each of these to a no. That's a yes. That's a yes. This is a no. This is a no. And I believe she had me set this as a no. And I'm going to call that limestone. Cool. Okay. So now I have my data. If I look at this, I have my yes, no. There's my 1 is my limestone, my 0 is my not limestone. And so then the real power of, so you're going to go through all of that, getting all of your data into kind of this 1, 0 set of parameters. Remove. So now I have, oh, I think I removed the wrong one. No, I didn't. Yes, I did. Whatever. You'll get it. Okay, I'm going to remove that. No, there's my limestone. And then I want my elevation, which would be, I don't remember now. See, this is why naming things really well is very helpful. Reclass elevation, that might be it. Let's look and see. Nope, that is not it. Well, I'll find it later, or not at all. Okay, so you're going to convert that to a polygon, and then you're going to reclassify to keep just your limestone. And then you're going to reclassify the vegetation. You convert that vegetation to raster using the density field. And now, so now when you're done, I'm going to have 1 is good elevation, one is limestone, and one is the density. So then I can use what's called map algebra. And map algebra is where the real power starts to show up. So because I have used the same size grid cell and I've used the same extent, my layers are going to stack up exactly. And then I can use my Boolean logic or my map algebra to say, okay, I want only the ones that are in all three of these, right? So if I stack these up and I use, you're going to use multiplication. So let's say this is soil and this is vegetation, and the ones are the ones I want to keep. If I multiply these across, I end up with only the places where both of them are a 1. 1 times 1 is 1. And in your case, we're going to use 3 different rasters. And you're going to multiply all 3 of them using map algebra, and you're going to end up with the areas that have good elevation, good vegetation, and good tree cover. You can also do addition. And so sometimes map algebra does addition to say, okay, the ones are my are not as desirables as the 2s. So the 2 has everything that I want. The 1 has just one of the things that I want, right? So let's say you did that. I think you're going to use that when you do the Sturgis finding a cabin. So you're going to have things that say, if it's this elevation, that is 1. It can be a little slopey, and that'll be a 2. And if it's a little more slopey, I'll keep that at a 3. So when you add those up with your aspect, the highest number or the lowest number is going to have more value. So you can do that sometimes, so you don't just have a yes, no, but you have multiple options. So here's what map algebra would look like. I'm going to set my output as Snail Habitat, and I have my ones of elevation, my ones of limestone, and my ones of trees. And I had some trouble running this. I kept getting error messages, so I had to start ArcMap and start again, and then it worked fine. Price has a note on the next page that says if map algebra won't work, here is an option for you. So this apparently is glitchy for lots of folks. But you can see that I have a formula in here that is just trees times limestone times elevation. And it was easy just to double-click trees, hit the multiply, double-click the next layer, and then it gave me my output. And so when you're done, I'm going to have Snail Habitat as 1, not Snail Habitat as 0. Right? So I end up with that. Just really clean and a lot faster and less processing than you had to do with the clipping, the intersecting, the merging with vector. The second part of price talks about how to cite a road or how to cite a cabin, and you're using Euclidean distance and direction. So you're going to start with a digital elevation model, I believe, yeah. And you're going to try to find the shortest distance between 2 locations and what direction. So this is the kind of stuff you would use if you wanted to figure out what's the fastest way to a school, not using network analysis, but using grid cells. And you can put in costs for elevation. So we talked about that. If there's a high hill slope, that's going to be a cost, and you can model that in. So in this lab, you're going to take a road layer, and you're going to use the Euclidean distance function to make a raster that shows how far each grid cell is from the road. And so grid cells that are on the road have a value of 0. So I could select all of the road values of 0 and actually get a raster of just the road. But when I did the Euclidean distance, I can see that within 275 meters, it shows me, where that is within the road. Here's the next value for distance. And so I could use this again in the snail habitat and try to say I also only want habitat that is so far from a road. So if I put the roads in there and then use the Euclidean distance, I could end up having a 1, 0 if I reclassified this and then add that into my roads. So you're going to do this with trying to find a cabin that is not near a road. And then you're going, so when I ran that Euclidean distance, I wanted to find all of the areas that were roads that were greater that or equal to 300 feet from the road. And so that's this thing. So the purple is every piece of land in Sturgis that's 300 feet away from a road or greater. But you could also do a ringed buffer. So I would like to see these different elements of 200 meters, 400 meters, 600 meters, or 9,000 meters from the road. So that gives you other options. So you're going to work through that. Oh no, this is still the snail. Forget Sturgis. We're still working on the snails. JBIT. Yeah. So if you wanted to figure that out, you could say, you know, the prime habitat is all that other stuff plus this number 4, which is furthest areas from the road. So you're going to go through all of those pieces with the snail habitat. And then you're going to switch to Sturgis, which is looking at the DEM and taking a model of the slope. So when you run ArcGIS raster analysis, spatial analysis, you're going to go to surface, and then you're going to run the slope tool, and that will spit out an image that looks like this, and the symbology is inherent. It spits out this symbology so that it has the same kind of color scheme. So I could find my low slopes here as I think less than 10 is what she has you do. So she has you reclassify this for slopes from 0 to 10 as a 1, and above that not. And then I think she has you look at a viewshed. So we're going to use a viewshed. A viewshed creates a 1, 0 raster that shows things that can be seen from this tower. So you're going to have 2 fire towers, and you're going to position those fire towers, and then you're going to say, okay, if I'm standing in the fire tower, what can I see and what can't I see from this? And so you can see that everything in the pink is visible from the 2 fire towers, and the stuff that's in not colored is not visible. So they use this a lot to identify where can you cut the trees and still have a scenic highway. They do it in reverse, right? I need to leave trees along this edge so that people can't see the clear cuts. So you're going to go through making a fire tower or a viewshed. One of the things that density, that raster analysis is really fun to do or fun to use is to find out the density of things. So if we were looking at a bunch of points of burglaries, we could create a density of those burglaries that would create a raster of a hotspot. And it would look at all of the cells and figure out what is closest to the next cell and create this hotspot map or this density map. And she may have you do that a little bit. The last caution about this lab is that naming your grid cells can be more tricky than naming other things. Absolutely no spaces, and sometimes this is where people have gotten into trouble. If there is a space in your folder name or your flash drive name, sometimes even that can mess up grids. I think they've worked on that, so it shouldn't happen too much, but I had a couple people where their data could never connect because they had a space in the name way down the way. You want to look at, for the data that we're using, we can only have 13 characters in the name. That's the longest, but I seem to think that's not true anymore because I think I was making really long names. So you can play with that. That's still in the documentation, but it may not be true. So I just wanted you to have a sense of how you're processing these different files and why you're doing it. She doesn't talk about that very much in the lab. She just kind of has you do these different things. So it might be even useful to read through the tutorial a little bit before you start with that. And I think I posted a guide of what I want you to turn in for this. And then I will post what's due for the Esri tutorial later. But, yes? Noon today? That's probably left over from last year, so I will. This one is due on Friday. Yeah. And it took me, right. No. The Esri is due Tuesday. So we're still going to do the Friday, Tuesday thing, right? So I will check. I'll check Moodle. Just hang in for a Moodle update. Okay. All right.